Welcome to Lesson 5A, Heat Stress, Part 2. We are going to talk today about thermodynamics of the human body. Think of your body as a thermodynamic system. So I want to draw your body. You are a thermodynamic system, so you have heat transfer coming in. We'll do this in the standard thermodynamics way. So heat is defined as positive into the control volume. So your body is the control volume. You're doing work, lifting some kind of weight up and down. W dot is the rate of work that you do by the body. So it's positive if work done. And then inside your body, you have some capital U, which is the internal energy of the control volume. So this is the internal energy in your body. So from a purely thermodynamics point of view, we would write the first law of thermo as du dt equal q dot minus w dot. It gets a little complicated with the body because the work you're doing as you lift weights, or if you're running, you're not really lifting any weights, and that still is energy being spent. So we're going to group this W dot term, this rate of work done by the body, with the metabolic rate. So when you're doing work, M dot will go up, and it doesn't matter then what work you're doing, whether you're actually thermodynamically lifting a weight, or if you're playing basketball or tennis or something like that, or swimming, where there's really no weight being lifted. So we're going to basically group W dot with M, and we'll not worry about the W dot. So cross off W dot. Also, from a thermodynamics point of view, du dt is negative M dot. So we have these two equations, 1 and 2. The first equation is your standard first law, but we're ignoring the work done. We're going to instead look at rate of change of internal energy in your body, and that's due to the metabolic rate. So in other words, your internal energy is decreasing, that's why there's this negative sign, as you burn up that energy. We know how to calculate M dot for various types of people, body weights and sizes, etc. We talked about last time, various activity levels. So we can combine 1 and 2 together since they both have du dt on the left, and we end up with M dot plus Q dot equals 0. And so that's going to be the workhorse equation that we use. All we need to do is find out what Q dot is. We already know what M dot is for certain activity levels and for a certain kind of person. I have to stress that this is for steady state conditions. We're assuming that you're doing something constantly, like walking along or running, and so your M dot is some value, and then you have a Q dot that has to accommodate that. As you work, your body loses energy, and so the Q dot has to compensate for that. Thinking about this in words, we burn food and we generate a metabolic rate. And this energy goes into heat transfer from the body. So as you exercise, even if you just sit there as a couch potato, you are burning up food and you're making your cells warmer. And that warmth, that extra energy has to go out to maintain your body temperature, your core temperature, since you're a homeotherm. And so we can say that since M dot is always greater than 0, even when you're sleeping, you have a positive metabolic rate. And because of this equation, Q dot must be less than 0. So heat has to be transferred out of your body since Q dot is defined as positive when heat is transferred into your body. This is a check if when you're doing some of your calculations, make sure that Q dot ends up being less than 0. If it's not, that means that in order to maintain your internal temperature, you have to have heat coming in, which is not going to happen because you're going to freeze. We'll talk about that later. This is the equation we had, M dot plus Q dot equals 0. M dot's the body's metabolic rate, which includes your exercise and activity. Q dot is the net rate of heat transfer to the body. M dot is always positive, so Q dot must always be negative. There's various ways to gain or lose heat from the body. So let's just talk about some of these. Conduction. This would be like you're standing on the ground and your feet are touching the floor. So that's usually very, very small. So we're going to ignore this term. The only way I can think it's not small is if you're laying down on some kind of cold ground and then you're getting some significant conduction into the cold ground from your body. But we're going to usually be talking about activity. So you're always standing up doing something. Convection, air blowing over, can be positive or negative. It's usually negative. It's a cooling effect unless the outside air is hotter than your body temperature. Radiation, again, can be positive or negative depending on whether you are hotter than the surroundings or vice versa. Respiration can be positive or negative, again, depending on the outside air. If you're breathing in really hot air, you're going to be adding heat into your body, but most of the time, unless it's really hot outside, you're breathing out warmer air. So you're losing heat by breathing, just like you lose moisture by breathing. And then evaporation, this one's the exception to the rule here of being positive or negative. This one always has to be negative because this is due to sweating, and you can't gain any heat by sweating. You can only lose heat. It cools you off when you sweat. So if we ignore conduction, the first law up here, m dot plus q dot, we just split the q into these four. So m dot plus q dot convection, q dot respiration, etc. equals 0. What do we do now? Well, we have to come up with equations, and these are empirical equations that people have come up with over the years for all but the last term. That's the hardest one to calculate, how much evaporation heat loss by sweating. That one's hard. So instead, what we do is solve for q dot evaporation, and we'll call this the required value of q dot evaporation. So q dot evaporation is just negative of all these other terms. So this is the equation that we'll actually use. And then what people like to define here is something called a heat stress index. HSI is typically given as a percent, but it's a dimensionless quantity. It's the q dot evaporation required from this equation just above over q dot evaporation max, which we will need to estimate. So we can calculate this from this equation above, and we have to have an equation to estimate this, and then we can get our HSI. If your q dot evaporation required becomes positive, which would be impossible, remember this one always has to be negative, this q dot evaporation max turns out to be -2. You're losing heat by sweating. So you got two negatives generally. If HSI is less than 0, that means one of these terms has to be positive. Q dot evaporation max can't be positive, so Q dot evaporation required would be positive, and that would be hypothermia. In other words, Q dot evap required is greater than 0. You would have to gain heat by sweating, and you can't do that. This seems illogical. If it is impossible, how can HSI ever be negative? Good question, Jim. It's because we're assuming steady state conditions. You cannot maintain a steady state. So if I go back here, when I have this equation, this is steady state. And if you can't maintain that, du dt will start changing. Your u will not be a constant. When HSI is less than 0, that's a severe case of hypothermia. At the other extreme, if it's greater than 100, that's hyperthermia. Remember, hypothermia is too cold and hyperthermia is too hot. And what we're saying is that if the required evaporation rate of heat transfer is greater than the maximum possible, you can't do it. So your HSI goes above 100, and that means that you cannot cool yourself down rapidly enough, and you're in trouble. Your body core temperature will increase. And then everything in between. This is a strange table because it has like here 10 to 30 and then 40 to 60. What about 35? This is from ASHRAE, and I think the reason they did it this kind of strange way was just to say that this HSI is not very accurate. So if you're talking about 35.2, it's too many significant digits. When you're close to 100, only really healthy, physically fit, acclimated young people can withstand this. These are designed for 8-hour workdays, by the way. So if you're doing something with a HSI, heat stress index of 100, or even above 100 for a short time, you'll still survive, but you would get very hot. What we need now is equations for all these things plus Q dot evaporate max. And I'm not going to drive any of this. I'm just going to show you the equations. You have to be very careful with units. I can't stress this enough. These are what we call engineering equations, which I'm not a big fan of. But what engineering equation means is that you have to have all the variables in the correct units in order to get the correct answer. They have all the conversion factors built in, which is nice if you're just going to plug in numbers, but you have to be very careful that you're putting in the right units. All temperatures have to be in K, even though you'll normally be given them in degrees C, so you have to change. UA, this wind speed, has to be in meters per second. AS is the skin area, surface area of the skin. That has to be in meters squared. Relative humidity, you don't put it in as a percent, you put it in as a number. This is the craziest one. PV, the vapor pressure or the saturation pressure, has to be in kPa when you're doing the calculations for Q dot respiration, but it has to be in millimeters of mercury for the other equation for Q dot evap max. Here's a summary of the equations from the textbook and from these several references. HSI, of course, is what we're typically after in the long run. And these are the equations that we'll have to use to solve these problems. Again, these are engineering equations, so be careful with your units. This third one, capital K, is the fraction of exposed skin. It's exposed to the air. If you are totally naked, your K would be 1, meaning all of your skin is exposed. K has to be between 0 and 1. If it's winter and it's only your face showing, everything else is covered, you might have a K of 0.05 or something. Typically with clothing, like in the summertime, you have some shorts on or something, you might have a K of 0.7. AS equals skin surface area for a typical average man is 1.8 meters squared. And if you're very heavy, you could have more than this even if you're shorter. Women typically have a little bit less skin area than men. That'll be given to you for problems. And so K would be the AS exposed over AS. It's just a fraction of exposed skin. UA is the wind speed in meters per second. You'd have to measure that. TA is the ambient temperature. TS is the skin temperature. Typically, this is 35 degrees, except in extreme conditions. TW is an effective wall temperature, so this has to do with radiation. For example, if you're walking on hot asphalt in the summer and the sidewalk is extremely hot, the TW could be quite high. TG is a globe temperature. It has to do with radiation. It's the temperature inside an exclosure that's subjected to room conditions. You don't have to worry about that. That will be given to you. These have to do with radiation. You often see AS and K together because it's the exposed amount of skin. Another thing is all Q dot terms must be in units of kilocalorie per minute. So if you look at some of the tables, and we had kilocalorie per hour sometimes, and kilocalorie per day, all these equations will be in terms of kilocalories per minute. Let's look at this example. Let's suppose Pete is an average man. Now that makes it simpler because if Pete were not an average man, or if this was a woman, you would have to first calculate the metabolic rate for a certain activity for that particular person who might be bigger or smaller or a different gender than an average man. Pete is an average man playing basketball. These are the conditions. It's in the sun on a hot day. I give you the outdoor temperature, the relative humidity, 60%, so we would use 0.6 in our equations. The globe temperature is given, UA, AS, he's average, so he's 1.8 meters squared. Fraction of exposed skin, about 0.75. We want to calculate this heat stress index, or HSI. Let's outline how I did this. First, we look at table 3.6. We've used that a lot, and playing basketball is one of the items on that list. And for Pete, since he's an average man, MDOT is 565 kilocalories per hour. So we have to convert to minutes. So you just divide by 60. So 9.417 kilocalories per minute. Table A17, the vapor pressure table. We have two temperatures to worry about. Ambient temperature, 30 degrees C. We look up PV of water, and that's equal to P sat of water, saturation pressure, and that's 4.246 kPa. If you do the conversions, this is 31.84 millimeters of mercury. At the other temperature, skin temperature, 35 degrees C, we have PV H2O is 5.628 kPa, and that's equal to 42.21 millimeters of mercury. At this point, I'm not going to do all these calculations and spell them all out. All we're doing is plugging into all these equations up here. So I'm going to first calculate the radiation by calculating TW and then putting it into here. And I don't want to bore you with all these tedious calculations, but I'll do one of them just to show you all these temperatures have to be in K. So TG to the fourth plus all this stuff raised to the 0.25 322.04 to the fourth. You can calculate Q dot radiation and make sure you can duplicate this example problem, or else you'll be in trouble with the homework and the quizzes. So that's a hint. I strongly encourage you to duplicate all this, make sure you get the same answers. So I'll just give you the answers here. 376.64 K. Q dot radiation turns out to be 6.732 kilocalorie per minute. And then you just use these other equations. Q dot convection turns out to be negative 2.041 kilocalorie per minute. For respiration, Q dot rest, you plug that into the equation, and you should end up with negative 0.594 kilocalorie per minute. And then Q dot evap max, the maximum possible evaporation rate, negative 14.788 kilocalories per minute. And so finally, when we have all these, we can plug these into the required Q dot evap required equal negative M dot minus Q dot convection minus Q dot respiration minus Q dot radiation. Plug in all these numbers and you end up with negative 13.514 kilocalories per minute. Finally, we can calculate HSI is equal to Q dot evaporation required over Q dot evaporation max. We plug this and this in, the negatives cancel, you multiply by 100%, and you get 91.4% as your HSI. So Pete can play basketball at this level, probably not for 8 hours, but if he plays for an hour or so, he's probably okay if he's healthy and young. But this is considered severe heat stress. He'll be sweating like mad, but it's still less than 100%, so he's not at risk of dying even if he did this for 8 hours. I will show you one final thing. I put all my calculations in Excel to avoid any kind of algebra mistakes. I cannot stress this enough. Put all these numbers into your own Excel spreadsheet, MATLAB, whatever you want to use. Make sure you get my answer for this particular problem. These are the numbers that I gave you, and here's the same answer that we got. Duplicate my results in whatever software you want to use. If you get the right answer, you can be confident that you will get the right answer for the quiz. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.